Okay, so hi, I'm Matteo. It's Sijie. We are from Streamlio, with a startup that we are working on a real-time platform. Uh, but we are talking about Pulsar, which is a fast, durable, and flexible Pulsar messaging system. And we're giving a brief introduction, what problems it solves, why it was done, and so on, and the architecture, and then we're going for some demo and some use cases. So this is a project that started at Yahoo and was open source last year, and is a messaging system that was created to address some issues with existing solutions. So, for example, like in terms of durability, that one of the hard requirements was that the data has to be synced on disk, for example, replicated and synced on disk. You need to offer strong strong ordering guarantees and different kinds of derivative guarantees. For example, the most common one is at least one semantic, but we also support at most ones and effectively once, which is implemented as which is exactly once delivery implemented through guaranteed deduplication. Few of the differentiated features of Pulsar are around Geo-replication, which means that out of the box, you can set up multiple clusters and have data getting replicated from these different regions, and multi-tenancy. By multi-tenancy, we mean that at Yahoo, we had one single cluster, one single instance of Pulsar that was serving around 80 teams. That means that we have all kinds of features to support authentication, and I'll get in details later what we do for multi-tenancy. And another differentiated feature is low latency. So we've been talking about that we have durability, but even at these strong durability guarantees, we have to guarantee that the published latency at the 99th percentile should be around 5 milliseconds. In designing this system, we also tried to unify the messaging model. That means that in traditional Pulsar messaging, you have topics and queues, which have different semantics. For topics, you can have subscription. Queues are more like point-to-point delivery. So we tried to unify the same concept, these two concepts, into a single model. And a brief mention about the performance. It's a system that it can scale both vertically and horizontally. So on a single partition, so you can have topics and you can have partition within topics, but on a single partition, you can reach 1.8 million messages per second with low latency as long as there's more messages. But at the same time, you can scale to millions of topics. And just to give a brief idea, so this is a system that has been in production for more than 3 years at Yahoo, and it has been open source last year. And it's powering most of the critical Yahoo products like mail, finance, other exchanges, and Flickr, all the images uploads and workflows. And it's also powering like a platform themselves. So at Yahoo, we built distributed databases on top of Pulsar, so that use Pulsar for all the replication, both within the same region and across different regions. So it is the important point here is that it's on the critical write path of many operations. So if it is down, there is a lot of revenue loss per minute for which you cannot publish on Pulsar at Yahoo. Since it's a multi-tenant system, so we have one single instance that is serving like all these very different use cases and workloads, and there are around 80 tenants for this hosted solution. And within the system, there are like around 2.3 million topics, and with a flow of 100 billion messages per day, which is around 1 million messages per second. And all this with full message replication across 8 data centers. So again, that was a hard requirement. So most of the Yahoo products are in very different data centers, and data gets produced in all over the world, and it has to be replicated into different places. So a brief architecture view. The biggest difference from other messaging systems is that we have 2 layers in the system. We have 2 layers that one is dedicated for serving, which is the broker, and the second layer is bookies, which is Apache Bookkeeper, and these are storage nodes. That means that we have separated the storage and the serving of the data, and there are several advantages in doing that. Primarily is that you can scale each layer independently. So for brokers, typically the bottleneck will be on the CPU or the network traffic, if you have a lot of consumers. For storage, typically the bottleneck is on the I/O or the disk capacity. So depending on your workload, you can increase or decrease depending. Secondly, having 2 layers decouples where the data is stored from where the data is accessed. And that ensures that, for example, a broker it has no durable state on disk. So a topic is served by a single broker at a given point in time, but this topic can be moved very quickly to another broker. So I can add capacity, or if this broker dies, traffic will just move to another broker. And the same happens at the storage level. So at the storage level, a single storage node does not store all the data for a given topic or partition, but this data is broken into multiple segments, and these segments are spread across all the available storage nodes. That means that if I need to expand capacity, I can just add more bookies, and they will ramp up in traffic. The same thing with brokers. So if a broker is overloaded, I can just add more brokers, and the traffic will be automatically shifted to these new brokers that are not overloaded. So the operation at large scale are very convenient. So we talk about Bookkeeper. So we say that the storage component of Pulsar is Bookkeeper. So Bookkeeper is an Apache project. It's Apache Bookkeeper, and has been around for a while now. Is a project that came from Yahoo Labs as well, and it focuses on one thing, and it does that very well. So Bookkeeper is a replicated log storage. It means that you can create logs, manage them, and you can append entries into these logs. These logs are replicated. There is repeatable read consistency, and it's very high throughput and low latency, and highly available. As long as you have 2 storage nodes, you can write your 2 copies, and each node can store a lot of logs, which we have 1 log per topic. So it is very efficient to have like a high number of topics and a large concentration of logs per storage node, because of the storage model of Bookkeeper is very efficient in treating that. It has a journal, it has a lot of indexes, so it's a very sophisticated storage engine. And one of the most important thing about Bookkeeper is, apart from the rest, of course, is I/O isolation. So it provides I/O isolation between the write path and the read path. That means that you can write. It uses different devices. So the writes will go on a journal, and then get stored in background to a storage device, and all the reads will come from a storage device. That means that even if you have readers that are maxing out the storage device, you can still write with low latency and high throughput. And that is a key requirement for multi-tenancy. Just to make a quick visual difference between Kafka and Bookkeeper with Pulsar. So in Kafka is a system that is partition-centric. So you have a partition, and a partition is like a monolith. You cannot break a partition. And the partition needs to be stored entirely on a single broker. Now, if basically your storage is dictated by a single node disk, you cannot store more than that data. And also, if one broker dies, you have to physically copy like terabytes of data from one partition to bring it up another copy. And you can expand capacity easily, because when you expand capacity, you have to copy like terabytes of data into this new broker to make it serve the partition. While in Bookkeeper and Pulsar, the way we use Bookkeeper is we create multiple segments. So the same partition is broken down into segments over time. So every X minutes, you get a new segment. And this segment gets reassigned to randomly to the available bookies. So each bookie doesn't own, a single bookie doesn't own the whole story of a single topic or partition. But rather, these segments are scattered across all the available nodes. That also means that if one bookie goes down, the writer will just pick a new bookie and continue from there. And Bookkeeper internally will have a way to reform the replication factor of 3 that was required. So that's, and the same way, that is because that if we bring up a new bookie 5 now, the next segment X or segment Y will get allocated maybe on the bookie 5. So the write rate across all the bookies is very equalized. So going back to the messaging part, we say we have worked on a messaging model. So we try to unify the concept of topics and queues. So the idea is that you want to decouple from where you produce the data and how you consume the data. You should then be aware of how the data is consumed. So you produce on a topic. And when you consume, you can create subscriptions on this topic. And you can have different types of subscriptions. For example, you can have exclusive subscription, like subscription A, that allows only one consumer to consume. And this consumer will get all the messages in order. And is the only guy that is allowed to consume. At the same time, on the same topic, you can have a multiple subscription, as many as you want. And subscription B will consume all the data again. And in this case, it is a shared subscription that allows multiple consumers to consume. And effectively, this is a queue. So each consumer will get a third of messages in this case. And you can have basically as many as that. We also have failover, which is like active master slave with one only active. So a lot of features we have in the Pulsar client library. We have like Java, C++, Python APIs. We also have a WebSocket API service. And all these 3 libraries in 3 languages are like they have feature parity. They have been testing production for a long time. Even Python is based on C++, which is very mature. And at the client library level, we offer partition topics. So you have the logical view of a single topic, which internally the client library will know how to route messages to a given partition. And at the same time, the consumer will consume from all the partitions. And it will also handle the assignment for if you want to retain ordering within partition, you can basically configure failover mode, and it will assign one consumer per partition. Or if you don't care about ordering, we could just consume from all the partitions. We recently added also a Kafka compatible writer API. That the idea is that you can just take an existing application that was written with Kafka and just swap the jar and change the configuration, and we'll be able to publish and consume from Pulsar without any code change. The client supports transparent batching of messages and compression, and it will also compress the whole batch if you have both enabled. And we have TLS encryption and authentication with mutual TLS, and there is also support for end-to-end encryption. That means that you can encrypt the data at the producer level, and data will flow encrypted to the broker, it gets stored encrypted, and then consumer will have the key to decrypt it. So effectively, you don't have to trust the system for the security of your data. We talked about before about multi-tenancy. So at a high level, for multi-tenancy, you want to have multiple teams doing multiple different workloads, and you want to avoid having them to interfere with each other. And what you achieve with multi-tenancy is that you have a single cluster with less operational overhead, and you don't need to have like every team to understand how to deploy it and how to maintain the system. So at the very high level, you need to have things like authentication and authorization, you need to be able to say that these topics are belong to have like namespaces so that these topics belong to this team. This team can handle all its own provisioning, can change the configuration, and can authorize these machines to publish or consume from this topic. And all these operations need to be exposable through an API, like provisioning and all this kind of stuff. But under the hood, you need different level and different tricks to achieve multi-tenancy. And in the name as the first one, we talk about bookkeeper. So since the most common thing in messaging system is that you build backlog. So consumers are down for 3 hours. You have to back up messages, and when they come back up, they will drain it. Now, if they read from the same disk that you're writing into, basically, you would have like high latency and lower throughput on the write, so that will impact all the tenants. But in Bookkeeper, since the two paths are separated, basically the latency will stay flat, even when the readers are draining the backlog. And you can really max out the disk, and nothing happens. So this is at the I/O level. At the broker level, what we do is that we have different kinds of soft isolation in terms of like storage quotas. There's also flow control and back pressure at every stage in the system. And there's also optionally like rate limiting. You can set a rate limit for these kind of topics, for these tenants. And that's useful also like to enable that dynamically and to increase or decrease depending on the conditions. And finally, there is also support for hardware isolation. That means that you can constrain some tenants to be on a subset of brokers. And you can say that these brokers also are using a subset of bookies. So you can choose how far do you want to go with isolation. So isolation is something that is like creating a lightweight cluster within a cluster. So the idea is that you don't want to do it always, because it defeats the purpose of multi-tenancy, but is a very convenient tool to have when there is an outage, for example. So if for example, if some tenant is misbehaving, is causing trouble to other tenants, you can just quickly move it and reduce the problems until a proper solution is applied. The other feature that we think is a key differentiator for Pulsar is Geo-replication. So this is out of the box. You can configure multiple clusters within a same instance, and you can basically just configure, say, I want my data from this namespace, all the topics I want them to be replicated on region B. And tomorrow you just add the new data center. You can just say, change the configuration at runtime, and data will get replicated into region C as well. And this is full mesh replication, so you can, on a single topic, you can produce from any region and consume from any region. And this is something that is not some external tool. This is integrated into the broker flow. So all the guarantees are in there, and it's integrated with the stats, it's integrated with every topic concept. And after this, I will leave it to Sijie, which will illustrate some demo of Geo-replication and stuff.
Thanks, Matteo. I think Matteo gave an overview like how Pulsar looks like and how Geo-replication looks like. So let me just show you a quick demo. But this is more. Before I come here, I set up a Street cluster in Google Cloud, and that is basically in US Central and European West and US East. So basically 3 clusters. And sorry, this is basically how So this is basically a Pulsar dashboard, and it's available in any open source. So the 3 cluster I set up is basically European West and US Central and US Central East. And this is a 3 cluster. And this is how it looks like. And it basically gives you all the information about how data flowing from one data center to the other data center. You can see how data is coming from remote data center to local, and how data is flowing out. So this is give you the cluster view, how a global cluster looks like. And as you can, if you want to set up more and more clusters, you would just show up like this. And besides cluster, the Pulsar topic is basically is the unit is topic, but going down into a topic, it basically, if you take a look at the topic, it's just not a name. It's basically it has a hierarchy, and the hierarchy is typically comprised by 3 components, and the first component is basically a tenant to represent a tenant. And the second one is represent if this is a global topic, and this is a namespace, and under a given namespace you have all the topics. So you can control how people want to see this topic by granting different permissions. And this is like a flat view about how many topics you can see in a cluster, and you can see the traffic in and out. And if you want to see like actually how many tenants, like I create some of the topics represent for different tenants in a large organization. For example, if you have a group called data serving and a group about data marketing and product safety, they are just different teams in a large organization. And once you have a tenant, you can create different of the namespace. And these namespaces are managed by different teams, and you can grant permission to different tenants. And let me just use the marketing one to show, okay, this is like basically 2 different namespaces. One is for ETL, the other is for ads campaign, something like that. And in this property view, you actually can see the aggregation rate and throughput and how many messages are in the backlog not being consumed. For example, the second one in the market, there are about 760 megabytes not consumed. And if you drill down into namespace, you will see where it comes from, which namespace. And then if you're going down into the namespace, you will see the topic and where the data has been accumulated. So this is give you an idea how Pulsar dashboard looks like and how it has been used in Yahoo for supporting different tenants.
Can we see the tenants somehow? Because this doesn't show tenants.
Oh, sorry. The tenants in our Pulsar system is we call it a property. So this is the property is a tenant. Yeah. So you can think about the marketing. It's actually the property, and which is represent a tenant in an organization.
Are topics of government properties?
So all the in Pulsar you can create namespace, and under namespace you have the permission to create as many topics as you want in the namespace. So all the permission control, all the storage quota, all the rate limiting are applied in the namespace level, so it doesn't going down into individual topics. So this gives some kind of trade-off between the flexibility and also the manageability. So you can control in the namespace level and then give more.
Multiple properties can access the same namespace?
By default, if you namespace is created under a given property, and so all the permission are default to the tenant itself. But if you, like say, there's a collaboration between 2 tenants, then you need to grant the permission to the other tenants. In this example, I just create this as a admin account, so you can see all the tenants and also all the namespace.
Is there any notion of global topics that can be accessed by everyone?
Matteo? Oh, so the question is there any way to create a topic that is globally to all the tenants? I think this is more about if you create namespace and then grant a permission to all the tenants. So, but I think by default, so the answer is, I think by default you need to grant access control to the namespace in order to that the tenants to access. And there's ongoing proposal in Pulsar community to propose some kind of public access on the namespace once you authorize. And besides, this is basically a view how it looks like where the data has been. Sorry, this is a broker view, and this is how the data has been accumulated in different brokers. And this is basically an admin dashboard. And besides that, I think Pulsar also provide a lot of stats and collecting by different plugin stats provider. And I just use Prometheus to collect all the stats and draw all the stats in a Grafana dashboard. And this is how it looks like. I think probably I already stopped the traffic, but this is, oh, this is a different cluster, okay. Okay, so this is basically, I think I have two publishers is publishing into two topics. One is data serving, one is marketing. And this shows the publish rate and also show the local deliver rate. And this is throughput by the bytes per second and also the deliver throughput bytes per second. And also I create a consumer, I stop it, and cause some kind of backlog in the topic. And this, you can basically see how many data has been accumulated in one of the topic. That means someone has stopped consuming from the given topic. So by using this dashboard, all the metrics provided by Pulsar, you can easily, quickly find what's wrong with for a given topic for a given namespace. So hope this give you an idea how Pulsar looks like. And sorry. So let me try to make a conclusion about what Pulsar really it is. It basically is. I mean, a lot of people asking what's the difference between Pulsar and Kafka. In short, I think it's fast, durable messaging and backing by log storage. So in terms of fast, durable PubSub messaging, is more focused on messaging. It supports both queuing and also PubSub, and it focuses on messaging dispatch. And it removes data as soon as all the consumer has acknowledged it, and there's no retention has been kept. So this is on the messaging side. And on the storage side is it leverage scalable log storage, and which is Apache Bookkeeper. It store the message durably and guarantee no data loss. And because it's backed by a durable, scalable log storage, it can do a lot of things that storage already provide. You can rewind the data. So rewind the consumer or rewind the reader back into any point of the time in the storage. So it allows you to do things like backfill and also do stream computing. And also it carry all the features coming from log storage, how you distribute data, how you balance the traffic. And the separation of the messaging and storage itself, it actually create a lot of key features to the success of multi-tenancy. So this is basically how it's different from Pulsar. So Pulsar different from other messaging system. And as in Streamlio, we choose Pulsar as the messaging system, but in the real-time solution, we think you not only just need messaging. Messaging will become your source and also your sink, but additionally, you need storage because during stream processing, if you want to do stateful processing, your stateful job need to persist a lot of intermediate results. And also, if you want to support exactly once you want, you probably need a log storage to generate all the changes happening in a streaming job. So that's what we think in a real-time solution. It basically comprises of 3 components: is messaging, storage, and compute. And we don't want Pulsar to do everything, like because in the market, in the open source area, there's already tons of very mature stream computing. And the vision of Streamlio is try to get the every best project in different area to build an end-to-end real-time solution to simplify the customer's use case. So this is basically our talk about Pulsar. If you want to, Pulsar is still new. If you want to learn Pulsar and also Bookkeeper, you can follow this open source project. They are all in Apache now. And we also write a bunch of the blog posts about the history about Pulsar, Bookkeeper, and also like why Bookkeeper provides a good foundation for log storage. And if you are curious about this, you can also check out this blog post. Sorry. And this is what we are working on. And hopefully we want to build a fantastic real-time solution to our customers. So yeah, thank you.
So are you positioning this as an alternative to Kafka?
Oh.
Are you positioning this as an alternative to Kafka?
How do we positioning this as an alternative to Kafka, right?
Are you positioning this as an alternative to Kafka? Because there's no obvious overlap.
Yeah. So at Yahoo, I think this when initially when Pulsar was developed is basically like 3 or 4 years ago. Kafka is already there. But at Yahoo, we hit a lot of problems, like how to run this at scale and how to operate in a shared cluster, because we see in a growing organization, if you want to run Kafka in to keep with the traffic, you have to set up different clusters for your tenants. And this doesn't. This is not going to be a scalable solution for when the traffic grows. So that's why Pulsar was created. So I think yes, we go. Pulsar is we go directly as for Kafka as an alternative messaging solution. Yep. Yeah, and also one thing to add what Christian said is basically I think the strength the why like Pulsar is unique is basically geo-replication in multi-tenants has been built as from day one. All these features are kind of available in all the open source solution. And in Kafka, I'm not sure if you guys have been running Kafka with geo-replication. It has to set up additional Kafka minor maker, and this has been became like we heard from different users that it has become a problem when you want to set up with different with multiple data center, especially like if you are in IoT area, you want to set up edge to cloud replication, and you have to set up a lot of minor maker worker. And this, I think, this has been much easier in Pulsar because it's all configuration, and the replication is done actually in the messaging system, inside the messaging system. So you don't need to set up additional minor maker. So I think this is one thing it was got. But yeah, that's it.
What language is it written?
What's it?
What language is it written?
So the core language of the system is implemented in Java, and it's use native as the network communication, and it use a lot of direct buffer, and so I think direct buffer and also the native byte buffer pool to offload a lot of memory management into native language. So it tried to minimize the impact introduced by Java GC. And it turns out to be a very good result is when we produce the message in a very high throughput, we can get under 5 millisecond P99 latency with fsync. So basically, the data has been flashed to disk and fsync before acknowledge. So this is the latency what we get at Yahoo production. Okay, so the question is, in Pulsar, there's cross-region replication, and does Pulsar retain the ordering between cross-region replication? Okay, so the replication we explained this is an asynchronous replication. In the asynchronous replication case, we only keep the ordering per region. So because there's no global region as a leader, so it cannot define a global order across multiple regions. But because Pulsar is running as two separate layers, one is broker, the other storage, we actually can run Pulsar in a global synchronization mode. What does that mean is there's one broker will be elected as the leader for a given partition. So all the messages will be serialized by the broker, and this would guarantee the global ordering between multiple regions. And the storage layer, it will guarantee for a given message, you can write to at least 3 data centers and wait for 2 data centers to acknowledge. And because in the storage layer, it uses a parallel replication mechanism. So that means when you try to write to multiple data centers, it actually, so it's like more like a column bolt. And so when you just need to wait the majority of the data center to respond. So if a data center get slow, it doesn't impact the latency. And the other thing to call out here is when people are talking about synchronized geo-replication, people will think throughput would be killed because of the latency cross-region would be high. But it's actually not very true because latency and throughput are kind of two different things. If you send the request in an asynchronous way, you are actually pipelining all your requests coming from one region to the other region. So you can still get the same throughput as you can get in local data center. But the only thing is the latency would be high is because you need to do, this is the physical limitation between data centers. So this is something I want to call, yeah. Yep. Okay. Any other questions? Okay. Thank you, everyone.